Thank you to Professor Wahlberg and Professor Johansson for the opportunity and the invitation to come and visit Stockholm and KTH and give this talk. So I'll be talking about the title, Stability in Selection and Game Theoretic Learning. And just to give some motivation, you've probably seen this kind of motivational slide a lot these days in particular, is that there's a kind of a growing interest in the idea of networked decision systems. So in a network decision system, there are many interacting components, and these components, based on local information, are carrying out decisions. There need not be any single component that has full information. There need not be any single component that has full authority. So based on local information and local decisions and local interactions, we'd like to understand how this collective behaves. So here I have different pictures representing different types of networked interactions. And the thing that I want to emphasize here is that these network interactions run the spectrum from social interactions, so things like social networks and their evolution, to engineered interactions. So there's a lot of interest these days, for example, in autonomous systems, teams of autonomous systems and sensor networks. And then there's hybrid interactions. You can think of the transportation or energy networks as interactions between air traffic control. Also, the US just passed a law to allow unmanned vehicles to be in the same shared airspace as civilian aircraft, piloted vehicles. So we have interactions between human and machine systems as well. And they all have this kind of networked flavor. So some illustrations here of social networks, transportation, evolution of convention. The keyboard there represents evolution of convention. And when we adopt a particular convention, then that adoption has to do with not just the convention, but there's a social element. And the keyboard reflects competing technologies. So having the best phone in town isn't of any use if I can't call any of my friends on that phone. So my adoption of that phone depends on who in my network, which on my social network, who in my friends have that phone. And that's what this kind of picture represents. Then we have other pictures of data networks, sensor networks, and what have you. So one can choose to take a game theoretic approach to looking at these sorts of network decision systems. And so with that in mind, let's just review what are the basic elements of a game. So a game has different actors or players or components or agents. I'll use those words almost interchangeably, usually saying agents. And these agents have choices. And what makes a game is that agents have preferences over choices, but not just over the choice that they make, but the choice that others make as well. Okay? It's the collective choice that constitutes preferences. So when we do our commuting, for example, we have to choose a path to take from home to work. It's not a matter of which path to take. My preference on the path depends on the paths that others have taken. You can think also in auctions. The quality of my bid depends on the bids that others have given as well. When our decisions and when our choices are interconnected, our preferences are not only over our own choice, but they're contingent on the choices of others. And that's what distinguishes a game theory from optimization. You can think in optimization, we have preferences over our own choice, and we need to figure out which one to do. But in game theory, our preferences are over the collective. We need to figure out what to do contingent on what others are doing. And that's what makes a game a game. So in the modeling agenda, the descriptive agenda, when different decision makers get together with these sorts of preferences, we'd like to understand what would be the outcome. And Nash Equilibrium, which I'll discuss in a moment, is one such solution concept. So historically, game theory has emerged from the mathematical social sciences as part of what I'm calling the descriptive agenda. There's a social interaction that we'd like to describe. So it's a model of an existing system, like the technology adoption. There's an underlying network. How does one technology become, or does one superior technology become replaced with an inferior technology replaced with a superior technology, depending on the social effect. So those are the kinds of things that we'd like to model and understand. So the elements of the game, who are the players, what are their choices, what are their preferences, are things that we're modeled. We're inheriting it from the actual situation, maybe. And so then we'd like to ask questions of, is this a reasonable model? If we have data, does the data fit the model? Those kinds of questions. Now, what's emerging, though, in engineered systems is this prescriptive agenda. So when I talk about sensor networks, I have some flexibility. This is an engineered system. I'm choosing to view it through a game theoretic lens. And ultimately, I can decide what are the preferences. I can program these into the different components. So in the prescriptive agenda, game theory becomes the language for design of programmable systems rather than the language of modeling and description. And this is an emerging area. And then we have different performance metrics. How well does the collective do, and what information is required for decisions, things like that. But it's more design metrics than modeling metrics. So I'm going to give a review of, kind of a very brief review of game theory, but this is the main message in the entirety of the talk. When different decision makers get together, historically game theory has prescribed some sort of solution as the outcome, and say Nash Equilibrium is the outcome. And what the message of the talk, it's a message that's been recognized over the years. If you think of the term Nash Equilibrium, which I haven't defined yet, when we use the term coming from systems and controls of equilibrium, we think of some dynamic process, and equilibrium is when this dynamic process is in a state of balance. Nash Equilibrium has described balance without describing any process. It's described a balance condition without prescribing what is the underlying dynamics. And again, this is recognized. So a quote of famed Kenneth Arrow, the attainment of equilibrium requires a disequilibrium process. How do they get there in the first place? If we're going to say that equilibrium is the outcome, how do they get here? And also, this is another quote of Brian Skirms, the explanatory significance of equilibrium depends on the underlying dynamics. And in defining the equilibrium in games, what will be the outcome when these different decision makers get together, no dynamics had been specified, just equilibrium. And these quotes recognize that the dynamics play an important role. And in fact, it's been recognized over the years, and here's a selection of different monographs that look at this dynamical issue. So the titles are Suggestive Evolutionary Game Theory, Individual Strategy and Social Structure, Theory of Learning in Games. And I'm showing also how these monographs have come out over the years from between the 90s and the 2000s and the most recently 2010. There are also different survey articles, and here these came out within the last 10 years, discussing this issue of if equilibrium concept is going to be the solution, what are the dynamics behind the equilibrium? And again, that's a reverse discussion than we usually have in systems and control, where we have dynamics and say what is the equilibrium. So in game theoretic learning, there's going to be we're going to model each individual agent as learning about its environment and reacting to its environment. And it's important at this point to state that the learning in the case of multiple learners is very different in the case of single learners. So what's the usual story in learning? And a very brief, kind of a nutshell description is that there's an agent interacting with the environment. They have choices, and they need to figure out what's the best thing to do. So through repeated interactions with an environment, I can figure out over time, by experimentation, what's the best thing to do. Why? Because usually we think of the environment as a stationary entity. So what worked yesterday is going to work today. Maybe there's some statistical variation, but generally I can do experiments and figure out over time what works. Now, if we take the single agent story and try to map that to the multi-agent story, it doesn't quite work because the environment is other agents. So if we think from decision maker number one's perspective, they want to learn about their environment. They're interacting with their environment. Who is their environment? Their environment is other decision makers. And other decision makers are trying to learn about their environment. So you can think that if you and I are engaged in this situation, while I'm trying to figure you out, you're trying to figure me out. But from either of our perspectives, the environment is non-stationary. Okay, we're both moving targets. So we can't just port single agent learning ideas and plug it into the multi-agent case. There can be kind of implications for that. So these kind of ideas were explored over the years. And one idea that came out in actually right around 1950 was a proposal of what the dynamics could be. It's not a statement of what the dynamics are, but rather a plausibility argument. These are dynamics that could lead to a Nash equilibrium. So and it's been analyzed over the years and it's played a kind of important historical role. So it's called the fictitious play, and probably these days it would be named virtual play. But the way fictitious play works is as follows. So suppose you and I are engaged in a game, and you have a choice between left and right, and I have a choice between left and right. We need to figure out day by day, what are we going to play, left or right, okay? So we're having a repeated interaction. We meet each other in the hallway every day, and we choose left and right. And so fictitious play does the following process. So over the course of time, what I'm going to do is I'm going to keep track of your past choices. And I'm going to build a histogram of your past choices. So in other words, I'm going to use that histogram to form a probability. In my mind, I'm saying, this is the percent time you've gone left, this is the percent time you've gone right, based over our history of interactions. I'm going to use those percentages to model what you're about to do. So if we've played for 100 days and you went 60 days left and 40 days right, my planning for tomorrow will be based on the perception that you're going to play with 60.6 probability left and 0.4 probability right. Now, you're not really doing that. You're not using a fixed distribution, but if you were using a fixed distribution, then what that would do, if you were indeed a stationary environment, over time I would figure out your probabilities, and over time I would play effectively against you because I figured out your probabilities. But you're not doing that. You're doing the same to me. You're watching my actions, and you're keeping a histogram of my actions, and you're pretending that I'm going to use that histogram to generate an action and playing optimally with respect to you. So both of us are building these histograms, and neither of us are actually behaving in the way that we're modeling the other. That was called the fictitious play. It turns out that fictitious play does converge in certain situations. So for example, in a zero-sum game, where it's a direct competition, it converges. In games where there's two players and each one has only two actions, it converges. In a special case of games called potential games, it converges. There are different special classes of games where it does converge. But there are also instances of games where it does not converge, and I'll talk about one of these in a moment. But the Shapley fashion game, anti-coordination game, merry-go-round game, games you're going to find if you start looking at the game theory, these example games all have very sort of appealing titles. So in these three cases, fictitious play does not converge. So sometimes it does converge, and when it converges to a Nash equilibrium. So it gives some strength to Nash equilibrium as the prediction. These guys got together, they used this very intuitive process, and they led to Nash equilibrium. Therefore, I believe in Nash equilibrium. But then these games say they didn't converge, so maybe I don't believe in Nash equilibrium. It didn't converge in these cases. So let me give an instance of where interactions do not converge. And we're going to come back to this one also later. So their setup here is two players playing rock, paper, scissors. So you've all seen rock, paper, scissors. Actually, it's a perturbed form of rock, paper, scissors where ties don't equal 0. They equal some small perturbation. And both players are using some process, just reinforcement learning. And we don't have to say what that is now, but it's a similar heuristic of based on what's worked in the past, that's going to, whether rock, papers, or scissors has worked in the past, that's going to influence my probabilities of choosing rock, paper, scissors. So when both players are playing according to reinforcement learning, or simple rock, paper, scissors, what's plotted here is the probability of rock, probability of paper, and probability of scissors, what turns out to be chaotic behavior. So if either player was actually facing a stationary environment, they would learn that environment and play optimally rock, paper, scissors against that environment. But what happens here is they're both learning. One is learning about the other while the other is learning about the one, and it turns out that their evolutions of their probabilities is chaotic. And this paper that appeared in the Proceedings of National Academy of Sciences presented this example and made this very strong statement. Economists have noted the lack of a compelling account of how agents might learn to play a Nash equilibrium. This is the modeling question. Why do we believe in Nash equilibrium if it doesn't emerge? And he says, our results strongly reinforce this concern in a game simple enough for children to play. So that was the stability story, okay? The stability story, the title of the talk is Stability and Selection. The stability story was when interacting decision makers get together, will they result in a Nash equilibrium? And there's been some algorithms proposed where they do, sometimes they don't. And now I'm going to talk about the selection story, and then we're going to all put it together for our agenda. So in the selection story is about, we do believe in Nash equilibrium, but sometimes games have multiple Nash equilibria. For example, in technology adoption, that's this typewriter game, technology A is superior to technology B. So the way to read these matrices is that there's two numbers. The first number goes to the row player, and the second number goes to the column player. So then if we both play A and A, then each of us gets 4 points. If we both play B, each of us gets 3 points. But if we miscoordinate, then both of us get 0 points. So technology A is a superior technology than B. In the technology game, both of us choosing A happens to be a Nash equilibrium. Both of us choosing B happens to be a Nash equilibrium. There's multiple Nash equilibria. Which one should we believe in? If we want to believe in Nash equilibria, which one should we believe in? Here's another game that's called Stag Hunt. And the story behind this game talks about the risk of coordination. So the story behind this game is that we can go hunting together for deer. And if we catch a deer together, then we split the deer and take it home. However, we can go hunting for rabbit or hare alone and catch a rabbit on our own without the help of the other. Now, if one person hunts for deer while the other one hunts for rabbit, the rabbit hunter takes home their catch, but the deer hunter goes home empty-handed because they required assistance. So what happens in Stag Hunt is that there are, again, two Nash equilibria. One of them is we both go for deer. The other one is we both go for a hare. Again, which one do we want to believe in? One of them leads to superior payoff, but there's something risky, and that is you can think of this almost as a cliff. If we both go for deer, okay, if we're getting deer, I'm taking home a payoff of 3/2. And then if I miscoordinate, then there's a drop-off from 3/2 to 1, okay, and going from deer to a hare. But the miscoordination from going to hare to deer is a drop-off from 1 to 0. You can literally think of that as a cliff, and that being both at hare and switching leads to a bigger drop-off than going from deer to miscoordination. Okay, so from rabbit to miscoordination is a bigger drop-off from deer to miscoordination, and that drop-off actually has a term, and that term is called risk dominance. So risk dominance is what is the drop-off I'm going to face, and payoff dominance is what you'd think it is. What is the payoff we're getting? So an equilibrium is payoff dominant if we're getting more payoff. It's risk dominant if the drop-off is great. And therefore, I'm very hesitant to risk that drop-off. So in Stag Hunt, stag is payoff dominant, but hare is risk dominant. There's a big drop-off. So there is a background in equilibrium selection, and some papers in the 90s and try to ask the question, which equilibrium should we believe in? So one approach that they took was to suggest a dynamic and let the dynamics decide. Okay, so the dynamic was as follows, that we're going to watch each other over a finite window. And I'm not going to pay attention to what you did over the entire window. I'm going to sparsely select sample days. Maybe those are the days that I remember. So I'm going to randomly select some sample days. And based on those sample days, I'm going to take an action. However, every now and then, I'm just going to experiment. So it has a stochastic element to it. Every now and then I experiment with some small probability. So we watch each other, we pick sample days, we react to those sample days, but every now and then we experiment. Because of the experimentation, we're going to be perpetually churning. We will never stay fixed at one configuration because of this underlying small probability experimentation. But what this paper showed is that when the probability of experimentation is small, the players tend to favor risk-dominant behaviors and not payoff-dominant behaviors. So they showed analytically that, for example, in Stag Hunt, these players, although they're experimenting, the probability of experimentation is small. They spend most of their time at hare, and vanishingly small time at stag. As the experimentation probability diminishes, they spend more and more time at hare and less time at stag. So which equilibrium to believe in? They proposed some dynamics and said, let the dynamics decide. And the dynamics decided. Risk dominance is the one that these dynamics believe in. So that's an illustration of the selection story. So we have stability and selection. Stability is, if we have a solution concept, what is the solution? Will it emerge? Selection is, if there are multiple solution concepts, which one will emerge? And now back to the different agendas. Well, we can think that in the descriptive agenda, stability explains how Nash equilibrium could emerge, and selection tells us a refined story. It's not just a Nash equilibrium will emerge, but which one will emerge. In the engineering agenda, they have, in the prescriptive or engineered agenda, they have different roles. Stability tells us how to design algorithms so that we get an outcome that we're looking for. And then the selection is, how do we design the algorithm so not just an outcome emerges, but it's the one that we want, an efficient outcome. Because like in the typewriter game, we saw that there was one behavior that was better than the other behavior. In the stag hunts, maybe an engineering agenda, we want them to go to stag. We do not want them to follow this algorithm. So we'd like to come up with different algorithms that select more efficient behaviors. So I'm going to give some overview of some recent work that's kind of setting the stage of transient phenomena and stability and selection, and some illustrations of selection and kind of things related to game theoretic learning, self-organization, and see some examples. Now, why am I kind of focusing on transient phenomena? So the idea behind equilibrium is that things are stagnant, things are not changing. And transient phenomena are phenomena that only appear when things are in flux. And what I want to emphasize here is the dynamic story, that although there may be multiple equilibria, it's really the transients that determine will we see them, and it's the transients that determine will they survive. Which one will we see? I want to emphasize the transient part. And the transient part is really part of the dynamic discussion. If we only talked about equilibria, by definition, there are no transients. And we want to say the transients can make or break what happens, and that goes back to the quotes that were mentioned earlier. So now to be a bit more formal, we have the same basic setup. We have a set of players. Players have choices, and we can represent the collective choice by a gathering of the individual choices. Sometimes we're going to represent the collective choice in this way, of AI, comma, A minus I. So that's to emphasize the split between the two. Their AI is the choice of agent I, and A minus I is the choice of everybody else. But we have payoffs. These payoffs reflect their preferences. So they're just some mapping from the collective choice to a number, a score, a reward, the bigger the better. And, but what makes a game again, is that the preferences are a function of everybody's action. So it's a mapping from everybody's choice. The reward for agent I depends on agent I's choice and everybody else's choice, and that gets mapped to a number. Now, I've mentioned Nash equilibrium several times, and now we'll state the definition of a Nash equilibrium. So a Nash equilibrium is a configuration that has the following property. So suppose we're all engaged in a game, one by one, the entire collection of us. We would be in a Nash equilibrium if the following held true. Go individually, and it's important individually ask each one of us, this is what everybody else did, would you like to change your mind? In other words, could you get a higher reward by changing your choice? But if you said no, then I'm going to move to the next person, saying this is what everybody else did, would you like to change your mind? If we go around the whole room and everybody says no, I'm fine where I am, given what everybody else did, we're in a Nash equilibrium. There's no incentive for a unilateral change. Now, it could be two of us can change our minds and both be better off, but that's not the definition of Nash equilibrium. Nash equilibrium is, individually speaking, as an individual decision maker, given what everyone else did, would you like to change your mind? If you say no, if everybody in the room says no, then we are collectively at a Nash equilibrium. Now, in game theoretic learning, we don't want to just assert equilibrium. We want to talk about how they will get there. So what we're going to do is we're going to play this game day by day, like rock, paper, scissors, or meeting in the hallway, or a stag hunt, or technology. We're going to play this game day by day. And then we're going to make our next decision based on the information that we have available. The information might be what you've been doing. For example, in the commuting game, the information might be a traffic report at the end of the day. I don't want to see what every other driver did individually by name. but rather I might just look at the traffic report. Or the information might be just how long did it take me to get to work without looking at the traffic report of other routes. So it could be in different formulations. We have different constraints on what is the information available. So every day I take an action based on the information that I have, and I'm allowing that to be a random action. I choose my probabilities as a function of the information that I have. So you can see that fictitious play fits into this format. The information that I have is what you've been doing day by day. From that, I build a histogram, and from that histogram, I determine what I'm going to do on the new day. Now, we're going to switch between discrete time and continuous time at our convenience. And there is a connection. And it goes as follows. We'd like to make what I described as a discrete time interaction with some randomness. And it turns out that one can make conclusions about the discrete time actions by analyzing a associated continuous time differential equation. And in fact, this method of ODE analysis has its origins here in Sweden by Leonard Lung as a kind of a pioneer of this approach. So here's an example. Fictitious play, it has a particular representation in discrete time with some randomness, underlying randomness. In continuous time, it looks like an associated differential equation. Reinforcement dynamics, where I increase the probability of choosing an action if it served me well in the past, has in continuous time another differential equation representation, which happens to be a replicator dynamics. I mentioned that to lead into the following result. So I told you that learning in the presence of other learners can be complicated. The rock, paper, scissors led to chaos, and this paper made a much stronger statement. So this paper talked about learning in the presence of other learners, but it also imposed a very natural restriction, and that is as follows. The learning rule of any agent cannot explicitly depend on the reward function of another agent. So I can watch what you do, but I'm not allowed to know why you do that. I can see that you went left or right when we meet in the hallway, but I don't know if you're trying to bump into me or trying to avoid me. My learning rule can only be a function of the observable actions, but not a function of your utility. Okay? They call that uncoupled learning rules. Fictitious play is a learning rule. I build your histogram and then take a move based on my utility and my observations of you. I don't use your utility function, your reward function, to make my decision. I use it implicitly because it has shaped your behaviors, but I don't use it explicitly. So they call those types of learning rules uncoupled dynamics. And this paper, which came out now 10 years ago, showed the following. There are no uncoupled dynamics that are guaranteed to converge to Nash equilibrium in all games. So it turns out that this uncoupledness can impose a severe conclusion. And in fact, they didn't need all games to prove this result. They proved this result using one particular game, and this is the three-player anti-coordination game. So there are three players, players 1, 2, and 3. They're both picking left or right. Player 1 wants to differ from player 2. Player 2 wants to differ from player 3. And player 3 wants to differ from player 1. So they want to anti-coordinate from the player in front of them. They can't all be satisfied because there's an odd number of players. And they showed that for this game, an entire family of learning rules cannot converge to Nash equilibrium. And this is a simulation, an illustration of what happens when you apply fictitious play to this learning rule. They oscillate between probability of left and probability of right, and you see these oscillations emerge in the associated differential equation. They just keep chasing each other. And they're using any uncoupled rule will lead to these sorts of oscillations. Well, it turns out that any uncoupled rule needs some qualification because it's not quite any uncoupled rule. And these are other simulations of uncoupled rules that lead to very different behaviors. So I'm going to now introduce an uncoupled rule that turns the oscillations in the anti-coordination game into convergence. It also turns the chaotic behavior in rock, paper, scissors into convergence of playing rock, paper, scissors with 1/3 probability. I'll give you a different uncoupled rule, and then I'll explain to you why this uncoupled rule doesn't fall into the category of the uncoupled rules that were considered previously. So the negative results about uncoupled rules not converging applied only to, you might call them static learning rules. So what do I mean by static? How can I say it's a static dynamic? Okay, it sounds kind of contradictory. So what do I mean by a static learning rule? When, say in fictitious play, I use your empirical frequencies, your histogram, to design my next behavior. I don't use how your histogram has been trending. So if your probability of playing left is 1/5, I use just 1/5. But suppose it has been flat and started ramping up, and now it equals 1/5, but it's 1/5 on a severe ramp up. I still use 1/5. Whether it was ramping down or ramping up, I use 1/5. I use it, so I don't use how, I use your behaviors, but I don't track trends in that behavior. So if I wanted to track trends in your behavior, that could still be uncoupled. I'm not using your utility function, but I'm just saying what are the recent trends. I'm looking at the entirety of your behavior, not just a sort of a static a snapshot. This picture didn't come out well, but you can just think, this is what I just described. This is what your behavior has been, but it is ramping up. So what I'm going to do, because it's ramping up, I'm going to build this myopic forecast. This is where you are. It's been ramping up. This is where I think you're going. Okay? That type of learning rule was not analyzed by the previous paper that said uncoupled learning cannot lead to Nash equilibrium. So we're going to introduce alternative learning rules, which we call these like marginal forecast learning rules. I watch what you're doing, but I look at trends, and I use the trends to shape my decisions. So in fictitious play, I'm going to react to not your empirical frequency now, but your empirical frequency and where it's trending. I don't know if it's really going to go there, but that's where it's trending to. It's still uncoupled, number one. But number two, it's purely transient. The idea of a trend is something that disappears at equilibrium. Equilibrium analysis will never consider trends because that's a transient phenomenon. And what we're showing here is that this transient phenomenon can make or break the convergence. Here I have an illustration of the usage of transient phenomena. We had snow in Atlanta last year, and for us that was a crisis. I think this whole city has 5 plows, and so this Georgia Tech even closed down for the opening first 3 days. But they had some traffic analysis, but if you look closely at this traffic, you see these kind of descriptions. So they give you a level, but then they gave a description underneath it. 5 and holding, 5 and building, 5 and clearing. So they told you the current level, but they also told you the trends with the anticipation that you're going to use this trend where the traffic levels are trending to make your decision. What will the traffic be like once I get there? And there is some history to using trends even in the setting of learning in games. So we can do a formal analysis of this. So we build this so-called marginal foresight learning. And here's marginal foresight fictitious play. I'm going to do a best response to where your frequencies are trending. In order to build where your frequencies are trending, I have to introduce auxiliary state variables, and that's what puts us outside of the class of learning rules that was the impossibility result held. So the impossibility result said uncoupled learning with this state dimension cannot converge to Nash equilibrium. If you allow me to increase the state dimension, here I'm increasing it through building a myopic forecast, allow me to increase the state dimension, then uncoupledness is not the barrier. It was the state dimension that was the barrier, not the uncoupledness. So here we introduce an uncoupled learning rule, which builds this myopic forecast, and you can do some analysis and determine when it may or may not converge. But in particular, it converges in the case of rock, paper, scissors. It converges in the case of the impossible game, of the 3-player anti-coordination game. It's still uncoupled, but it happens to converge. So transients made the difference in that, and not uncoupledness for that particular case. So that was transient behavior as related to stability. And we can also introduce transient behavior as related to selection. So now what we're going to do is continue this idea of reacting to trends, but not so that we can enable convergence. Actually, we're going to use it to disable convergence. If I have multiple equilibria and I start reacting to transients, an interesting thing happens. Some equilibria, all of the equilibria used to be stable in this setting. Some will become unstable, but others will survive. So by reacting to trends, what that can also have the effect of is choosing equilibria. What we've done now, we're not introducing trend reaction to stabilize. We're introducing trend reaction to destabilize some equilibria, and the ones that survive, that becomes an equilibrium selection device. So again, dynamics makes the choice. So in particular, we looked at a variation of reinforcement learning. So again, in reinforcement learning, the whole idea is to reinforce actions based on the reward that they've given you in the past. Okay, so if I just take an action, it gets reinforced. But does it get reinforced a lot or a little? Well, it depends on the size of the reward. So what we do here is we look at how the rewards have been evolving, but we also modify that to introduce how the rewards have been trending. So if I have an action that hasn't given me much reward in the past, but it's starting to trend up, then it gets a bonus, a boost in its reinforcement for that day. So through kind of this trend enforced, or we call it the dynamic reinforcement, one can then analyze which equilibria survive and which equilibria become destabilized. And what that's given us is that's given us a third way to characterize what are the surviving equilibria. So before, remember when we talked about stag hunt, we had payoff dominance or risk dominance. And one dynamic said risk dominance always survives. Well, through this type of reaction rule, again, it's just a natural modification of existing reaction rules. Through this type of reaction rule, we might get payoff dominance surviving, we might get risk dominance surviving, we might get something else. So we're just calling this, marginal forecast dominance, if you will. That introducing some players who use these myopic or trending to influence their actions will lead to some equilibria being destabilized and others surviving. And here I have just a few comments of showing that this foresight dominance is not a special combination of one or the other. We can get many different outcomes depending on how we tune the foresight parameters. So you can have something that's both risk dominant and payoff dominant, but it's not foresight dominant. So you can get equilibrium selection and perhaps tune equilibrium selection through the introduction of transient learners. So here's an illustration of that for a very simple network formation game. This has been called the connections model in some of the social network literature. And the way it works is as follows. Agents are going to form links to other agents, and these are directed links. So if I form a link to you, you can think that I'm a beneficiary of that link. So you can think of this as, say, reading papers. If I read your papers, okay, I don't need your permission. If I read your papers, I'm an immediate beneficiary of reading your papers, but I'm also an indirect beneficiary of the papers of others that you've read. Okay? So then my utility is how many agents can I access directly or indirectly? How many do I have access to? So if I form a link to you, I have a direct access to you, indirect access to others, add them all up, and that's my utility. Minus the cost of a link. It's costly to have a link. It's costly to do the reading. So I have to kind of subtract that cost. This has been called the connections model, and it's been analyzed in a few places. So here's an example of a very simple three-player network. Both of these are equilibrium conditions. So how do we test if it's an equilibrium condition? We'll ask, we'll poll each player, this is the current configuration. Would you like to create or sever any of your existing links? In both of these configurations, the delta or the V, every player will say no. However, the condition on the left, the equilibrium on the left, is more efficient in a certain way. And what do I mean by that? Every agent has access to everybody else. They're getting full benefit. So there's only 3 agents, so I have access to the other 2. Everybody's getting full benefit while only using one link. Okay? So they're getting the maximum benefit using the minimum maintenance, okay? Minimum number of links. Here, everybody has access to every other agent. However, this agent in the middle has required 2 links to get that access. So this is, from that perspective, less efficient. Okay? If we add up the overall rewards, the one on the left is superior to the one on the right in that everyone's maximizing with minimal effort. So it turns out that you can do this kind of analysis and ask which equilibrium survives. And it turns out that if the agents start reacting to trends in reinforcement learning, then this equilibrium becomes destabilized, and the efficient equilibrium in this case is the one that survives. So that talked about stability. We introduced dynamics, and in particular this sort of foresight marginal foresight to stabilize equilibria that were unstable. And we also talked about selection, where transient phenomena, and in particular a marginal foresight, can choose between equilibria. And now I'm going to talk about just a related matter that I could retrofit a game setting on this, but I'm not going to. And that you can talk about it at face value, but it also illustrates the selection phenomenon for just the general question of self-organization or self-assembly. So the self-assembly problem is a kind of abstracted, stylized one that we're looking at. And we can think that there are different atoms, and these atoms make connections when they bump into other atoms. And we'd like these atoms to get together to form a particular structure, to form a specified molecule. So we're allowed, though, to design the rules. We're allowed to design the chemistry of what happens when atoms bump into each other. Okay, that's the self-assembly question, is how do we give these atoms local programming rules so that when they bump into other atoms, based on their local information, they will ultimately form the configuration that we're interested in. So self-assembly has been analyzed over the last decade or so. And there are some standing assumptions. For example, there's some of the work assumes an infinite supply of atoms, that there's this large soup of atoms where we can keep drawing upon atoms and introducing them into the mixture. Also, the rules can be non-local, and here's what I mean by a non-local rule. So with each atom here, you see associated a letter, and that letter represents its internal state, its internal configuration. Okay? So what happened on the picture on the left is two subassemblies joined. Some of them were labeled B, some of them were labeled A. The middle ones got involved in a bond, and everybody changed their state. So if I join a chain, what we'd like to have is local rules. So if I have a chain, if an atom joins one end of the chain, that effect does not propagate its way through. The only change in state are the ones that were involved in a bond, or also the ones that are involved in a break. But if one atom joins a part of a chain, only those two are allowed to change their state. The remainder of the chain is not allowed to change their states. We want to keep that there's no inter-atom communication. The only communication is bonds and breaks, but there's no inter-atom communication. So here we see this picture on the right. Something joins. I'm showing one at a time joining. That's the simple rule that we'll talk about today. We have more complicated rules that we can introduce, but all of them are going to have this flavor. So when one of them joins, the only ones that were involved in the bond get to change their internal state. Another one joins, the only ones involved in that bond get to change their internal state. So we'd like to have a finite supply. We want to have local rules. Only bonds and breaks are they allowed to change their internal state. And then we are also introducing this reversibility. If something happened, it can be undone, maybe with low probability. So I'll play this movie and this movie is choreographed, while describing one particular learning rule, and then discuss the analysis of this learning rule. So we have some goal assembly. Here the goal assembly is a plus sign. And the learning rule is as follows. Each atom has an internal model of what the final assembly is going to be. So when they meet, they assume a role, and then they stick with that role. So we have a group of 3 have joined. That was a disallowed bond because they know that I'm an endpoint. Now these other 2 are floating, and now you see here we've reached a point where we're at a would-be deadlock. There's no way these 2 subassemblies are going to form a plus sign. So one has formed a role. They said, okay, based on our joining, I know the role I have. I assign a role to others that join me. I know if I have openings or not. So when they clashed, there was no opening. I know if I have openings, these two were singletons, so then when they met, they both had openings, and now they've assumed one of them is going to be the center and the other one's going to be a foot. But now we've reached a deadlock, so part of the learning rule that I'm discussing today, and there, again, we have some others, is that with small probability, bonds will break. So there was a disallowed bond, and now we're waiting for a small probability event for a break, and then a disallowed bond. And what can happen is finally we got out of that deadlock with this reversibility and formed a plus sign. So this is the algorithm. Only singletons join. When they join, they get assigned a role. When they're assigned a role, they know whether or not they'll have vacancies or whether they'll reject all future bonds. But with small probability, every now and then singletons break off. So we simulated that learning rule, and we've had a very curious observation. Now, the break-off probability is perpetual. There will always be kind of experimental break-offs. But when we simulated it, we first simulated it with 10 atoms in the soup. So the plus sign requires 5 atoms to make, so we simulated it with an integer number of the required atoms, 10 and 10, and we saw that they formed very quickly those two plus signs. Then we simulated it with 11 atoms in the soup, expecting to see this. We want to see 2 plus signs and 1 throwaway, but actually we saw this, okay, 3 throwaways, and they reached a deadlock. And so whenever we simulated an integer number of atoms, not an integer number, an integer number of the required atoms for the final assembly, they formed that requirement. When it was not an integral number of the required assembly, then we saw we wouldn't form the maximum, but rather we would have throwaways. And interestingly, it turns out that one can exactly analyze what's going on with the following assessment. So here we're going to introduce this idea of stochastic stability, and actually we've mentioned stochastic stability earlier in the talk today when I talked about stag hunt. There was some underlying experimentation, and I said for that particular dynamic, the players play rabbit-rabbit most of the time, and very little of the time they play anything else. That was stochastic stability. And here there's also the notion of stochastic stability plays a role. And we can say a state is stochastically stable if there's a minimum number of subassemblies. So what do I mean by a minimum number? If I have 11 atoms, how many things can I make? Well, I can make 11 units, but that's not the minimum number. I can combine some of them. And I can keep combining. What's the fewest number of units I can make with 11 atoms? It's 3. Anything with 3 units is stable, meaning that as the break-off probability goes to 0, we're going to see that a lot. Okay? Anything with 3 units is stable. If I have an integral number of the required, how do I make a minimum? If I have 10, I can make 10, 9 units, 8 units, but the smallest I can make with 10 is 2 units. That's the only thing that's stable. So we see exactly why the integral number of the required units works, but also we get a corollary to that, and it maximizes the number of throwaways. So if the final assembly requires a certain number of parts, say n atoms, like this one required 5, the maximum number of throwaways we'll ever see is n-1. So even if we have 1,000,000 atoms in the soup, if we're making plus signs, we'll never have more than 4 throwaways. The stable configurations are configurations that have at most 4 throwaways, but never more. So we have this sort of asymptotic efficiency as the number of atoms grows. These days we have even better algorithms that have better efficiency, but they're a little more complicated than what I described. So I mentioned this stochastic stability analysis, and it's really an intuitive notion. So I'd like to kind of give a trivial illustration of it for this kind of Markov chain. So what I've illustrated here is a 3-state Markov chain with transition probabilities that are epsilon dependent. So when epsilon equals 0, it's a very boring Markov chain. Just once you start at a state, you stay at a state. But when epsilon is non-zero, then there's going to be these low probability transitions. That's what we had in the experimentation for stag hunt. That's what we had in self-assembly. Epsilon equals 0 means no breakoffs. Epsilon small means a small probability of breakoffs. So you have these configurations, And now there's one in particular, though. The transition, the escape probability for state number 1 is epsilon squared, and the escape probability for the other 2 states is epsilon. So you can think as epsilon becomes very small, then although this Markov chain is going to be visiting all 3 states, it's going to spend most of its time in state 1, because it's much harder to escape state 1 than it is to escape the other states. And that is stochastic stability. We look at the stationary distribution and look at the stationary distribution as this mixing parameter, epsilon, goes to 0. And in that stationary distribution, there are going to be some states that survive and other states that we rarely see. We see all states, but there are going to be a subset of those states that we see regularly and others vanishingly small fraction of the time. That's what stochastic stability is. And what's interesting is that one can analyze stochastic stability without building the stationary distribution. One can infer which states will survive and which states won't survive without building this giant Markov chain and looking at its stationary distribution. And those are the tools that we use to make the conclusions for self-assembly. Here I have another kind of setup, and I'll just mention it briefly. I only have a couple of slides on this, where this idea of stochastic stability in games, it plays yet again another role. So then there's been an existing literature talking about the evolution of language. Now, language is a very strong term to use here. For us, a language is really grunts and whistles. So we have a set of objects. We map objects to expressions, and we also map expressions to objects. So a language is those 2 mappings. When I see something, what do I say? And when I hear something, what do I think of? And those 2 don't have to be aligned. It could be that, for example, here I have an illustration. And an illustration here is the mapping. P is the mapping from objects to symbols. And then Q is the mapping from symbols to objects. Here, this language is short of words. They have 3 symbols, but they only use 2 words. So even I can use all my words, I can hear all my words, but these 2 need not be self-consistent. And we like to ask, when our languages, if we impose some learning process, which languages will be selected? Will they be self-consistent languages? So we introduced some dynamics, and the dynamics work as follows. So we have some underlying network, and say a agent is picked at random. And what that agent is going to do, this is the simplest one, there are some more local versions. What that agent is going to do is they're going to see, this is the language that I'm using. How well can I communicate with society? Well, how aligned is my listening to society's listening? How aligned is my speaking to society's listening? And how aligned is my listening to society's speaking? And I'm going to compare that with the languages that are being used in society, and I'm going to pick a language that has high fitness. And now I'm going to do that with very high probability. So I'm picked at random. I look at my language versus the languages that society is using, and I pick the better of the 2 in terms of which one communicates with society the best. I do that with high probability, or with low probability, I mutate. Okay? Now, if we didn't have mutations, what's going to happen, if we didn't have mutations, there will emerge one superior language, and everybody will speak the same language. However, if we didn't have mutation, although we've all converged on the same language, it could be that our language is not self-consistent. That when we see something, we say something. When we say something, when we hear something, we think of something. But those 2 mappings are not self-aligned. And what we showed here is that if you allow for mutations, then not only are we going to speak the same language, but the language that we speak will be a consistent language. The only stochastically stable languages are the ones that are consistent. Without mutations, we'll all speak the same language. With mutations, we'll all speak the same language most of the time, and that language will be self-consistent. And that's a recent work. Okay, so final remarks. You know, really this is the two-word recap of the whole talk, is that in modeling network decision systems as games, dynamics matter. They matter in stability, they matter in selection. I didn't really talk about you know, convergence rates. How long does it take to reach equilibrium? And there is ongoing work on that and improving convergence rates. To improve convergence rates, we really take advantage of the engineering agenda, that we can program these sorts of learning rules. And you know, one conversation one can have is further exploiting the engineering agenda. For example, why don't we just introduce some auxiliary chatter or communication? If these agents can not just observe the actions of others, but maybe say a few words in the process, what can that do for stability and selection? But in the modeling agenda, you know, and this was an actual conversation that I had with some folks who worked in this area, I thought that reacting to the trend is a natural thing. Okay, we do it in controls all the time. It's proportional derivative controls. We couldn't stand up without it. And even in the market, you know, the trend is your friend. There are all these anecdotal things about trends. I thought reacting to the trends is local, is natural. The first conversation I had about this with someone in the field saying, why would anybody do that? Okay, it's so unnatural. It's concocted, they viewed it as. So, you know, so what constitutes a natural learning rule? Are these kind of things concocted or not? For the engineering agenda, it doesn't matter. We can be, you know, concocting rules to get the desired outcome. But I think that these results are relevant for the descriptive agenda as well, in that dynamics matter. And then we'd like to have a better idea of what's natural and what's not. And with that, thank you.